Hey everybody, happy Tuesday. It's Mr. Marquardt once again. Hope you guys are having a great Tuesday so far. One quick announcement before we jump into our lesson for today is that tomorrow is formative quiz number 7, so please make sure we are looking on its learning and getting that done if we are an all virtual students. Otherwise, if you're missing any other quizzes, tests, homework, all that kind of stuff, please get that in because the end of the quarter is next week. We are running out of time to get that stuff done, otherwise it's going to negatively affect us and our grades long term. So please make sure we get that stuff turned in if we're still missing test quizzes, all that kind of fun stuff. Otherwise, we're going to jump right into the lesson today. We're doing 523 recursive sequences. We're going to put the answers up for the homework real quick, and then we're going to jump on in. So if I can get my computer to cooperate with me. There we go. Next page, homework answers. Again, if you want to check those out, pause the video, check the filled in notes. Otherwise, we're going to jump on in. So next, 523, how else can we write the equation recursive sequences? Yesterday we spent a lot of time talking about arithmetic sequences, and we're going to build on that today. So today we're going to investigate recursive sequences. A term in a recursive sequence depends on the terms before it, and that's what we're going to start in with right now. So let's start by taking a look at 571. So 571, we've got the following sequence. We've got -8, -2, 4, and 10. As I look in between those terms, it looks like there's a common difference as we go from one term to the next. It looks like we are adding 6 every single time. So that tells me, first, that this is going to be arithmetic, because we are increasing that, or we are adding 6 to every single previous term. Again, it's a constant amount, so we're arithmetic. We're adding arithmetic A. I'm going to fill in our table with the exact same thing. So for our first term, we've got -8. Again, following our pattern, adding 6 as we go up, we've got -2, 4, and 10 for our first 4 terms. Our 0 term, we're basically going from 1 backwards. So we got to do the opposite of adding 6. So we're subtracting 6. We can start at -14 for our 0 term. So what are a couple different ways that we could figure out how to find the 10th term of our sequence here? So what is the way we could figure out the 10th term of our sequence? The first way is if we just filled out this pattern all the way across. If we've kept this pattern going 5, 6, 7, 8, 9, 10, and so on and so forth, we could do that to figure out the 10th sequence. That's one way. Second, probably the easier way, just find the equation of this sequence. So that's what we're going to start with. We're going to find the 10th term, but first we're going to write the equation. Our explicit equation is the one we kind of talked about in class yesterday that looked like T of n is equal to the difference between terms times the term number plus our initial term, which we called a sub 0 yesterday. Very similar to the equation of a line where it's y equals mx plus b, where the m and our difference, or the slope and our difference, are more or less the same terms. It's how fast those two things are growing, and the y-intercept and our starting value for our sequence are, again, basically the same thing. We find those two, we can find the difference and the intercept or our starting value the exact same way we would with the equation of a line. We're just changing the letters a little bit, and we talked about that again yesterday. So we want to find the equation for this sequence. Again, we know our difference is 6 because we are adding 6 between every single term. We know our starting value, or that 0 term, is right here, -14. We talked about that already. So that a sub 0 is -14. So we can say that our explicit equation for this particular sequence is T of n is equal to 6 times n, which is our term number, and then subtract 14. So that's our equation right here, which again, we should probably have down in part B, but I just did it up on top. So if we want to find our 10th term, that's saying n is equal to 10, because again, we know n is our term number like we have in our table. So let's plug in 10. So T of 10 is equal to 6 times 10 minus 14, which is equal to 60 minus 14, which is equal to 46. And we just found our term number, plugged it on in, and found our final answer for T of 10 to be equal to 46. Not 40. Let's fix that. There we go. 46. That looks better. All right, so now let's scroll down and look at C. So the next term after T of n is called T of n plus 1. So again, if we have t of n, we're adding 1. That's just the next term in that series. So if we want to find an equation, or we want to write an equation to find t of n plus 1, if you already know what t of n is. So if we already know what t of 1 is, or t of n is, and again, like we know t of n is 6n minus 14 from up on top here. If we want to write any recursive equation, again, one that finds us the next term in our sequence, what we can do is write it as t of n plus 1 is equal to t of n. So basically our function up here, and then we just have to add our difference on. So if we add our difference on, basically we're taking that next term and adding that same amount of growth onto our arithmetic sequence as before, which is the recursive equation for an arithmetic sequence. Again, we're taking that already original t of n, we're adding that existing difference on to find the next term of our sequence, or of our series. So if we do the same thing here, if we try to figure out what the next term would be specifically for this sequence, we would say, again, knowing that our difference is 6, that our recursive situation, or recursive equation for this sequence would be t of n plus 1 is equal to t of n plus 6. Because again, we're just taking that term value, we're adding our difference onto it to get to the next one, and this would be our recursive equation. Again, one that helps us find the next term, providing that we already know what the previous term was. So let's see how this works. So if we go to 72 on the next page, Alejandro used his recursive equation. T of n plus 1 is equal to t of n plus 6, which is exactly what we had on the last page, or in the last problem, from part C of 571, to write the following sequence. So does this sequence, or does Alejandro's sequence match the sequence from the problem in 571? So his sequence, 0, 6, 12, 18, 24. Again, we're increasing by 6 between all those terms, but something looks kind of goofy. Again, our sequence from the top of the page in 571 was -8, 2, or -8, -2, 4, 10, and so on and so forth. So very clearly they're not the same sequence, because we're starting at -8 in the original one. Here, Alejandro starting at 0 and then going to 6. So do these two match? That is very clearly no, they don't match. So where did Alejandro go wrong? So as we look, the one thing that really stands out to me is what's the biggest difference here? Again, the difference is the same between the two. Again, the common difference, they're going up by 6 between terms for both sequences, but Alejandro starts at 0. In the very first problem in 571, we started at -8. So if we want to fix Alejandro's equation and fix his sequence, what we have to do is we have to start. Oops, let's fix that. We need to start at t of 1 is equal to -8, which would help us get back on track. Or we could also start at t of 0 is equal to -14. So either we can start at t of 0 is equal to -14, or t of 0 is -8, which again were the first two spots on our table at the very top of the page. So if we start at either one of those two spots, then our sequence is going to match from there on out using that recursive expression that we have right here. So t of n plus 6 is equal to t of n plus 1. All right, so let's turn the page, and we're going to do a couple of practice problems together. I'm going to leave 73 for you to do on your own. I'll put the answers in the filled in notes, so be sure to check those out, but we're going to skip that one for the time being and come back to 74. Avery and Colin, they're still at it, again, because they started in 73, which you just finished, and then you're going to come back and watch this one or check your work later. But Avery and Colin are still at it. They've got, Colin wrote t of 2 is equal to 19, and then t of n plus 1 is equal to t of n minus 2. So here's our recursive situation. So we know t of 2 we want to help Avery write an explicit equation and then try to figure out if our sequence is arithmetic, geometric, or neither. So that's what we're going to try to start with. So again, we know t of 2. If we know an equation for t of n plus 1, again, when our number is inside our parentheses, what this is saying is n is equal to 2. So let's use that to find our next term in our sequence. So here, let's use this recursive equation to find t of 3. So we're going to plug 2 into this bottom equation. We're going to take that same number, plug it in for n right here. So here we have t of 3. Actually, I'm going to rewrite that. Let's say t of, because we're plugging in 2 for n, t of 2 plus 1 is equal to t of 2 minus 2. So now we have t of 2 plus 1, so this is t of 3. We know that t of 2 is equal to 19 because it says so right here. So we can say 19 minus 2. So the next term in our sequence, t of 3, is equal to 17. Let's do that one more time, see if we can figure out the pattern. Let's find the next term in our pattern, which is going to be t of 4. So again, if we use our recursive equation, we've got t of, well, let's switch the color here. One more time. We're going to switch the color. Let's go to t of, this time n is equal to 3. So t of 3 plus 1 is equal to t of 3 minus 2. So now we're at t of 4. T of 3 is equal to 17. When we subtract 2 from that, we know that t of 4 is equal to 15. So as we look at our three terms that we found, we've got t of 2 equals 19. We've got t of 3 equals 17. We've got t of 4 equals 15. So if we look, again, we're going down 2. We are decreasing by the same amount, so this is going to be an arithmetic sequence because we're like basically adding a negative number to our previous term. So we have an arithmetic sequence, and now we just got to figure out the equation for this one. So we've got our differences right here. It's a -2. We're subtracting 2 from every single term as we go down that. So we can start again with our general equation for t of n. So t of n is equal to minus 2n, and then plus our original value, a sub 0. So we still got to find a sub 0 here. Again, when we know we have an ordered pair or points and solutions to our equation, then we can just plug those in and then use that to find our starting value. So I'm going to use our original one. So t of 2 is equal to 19. So can we take 2, plug it in for n, t of n is equal to 19. So that's what we got to put in for t of n. So if we have 19 is equal to -2 times 2 plus a sub 0. So now we get 19 is equal to -4 plus a sub 0. Now we got to add 4 to both sides. So if we move this over here, we get 23 equal to a0, or a sub 0, or we know that our final equation, since we now have our starting value and our difference, which is -2, our explicit equation is a sub n, or t sub n, sorry, is equal to, t sub n is equal to -2 times n plus 23. There we go. Let's jump down to part B. So now Avery wrote t of n is equal to 6n plus 8. And we want to write the recursive situation. So like we kind of noticed here, our recursive situation up on the top, t of n plus 1 is equal to t of n minus 2. That minus 2 ended up being our difference. So if we can find the difference in our common difference in our t of n equation, then I think we can find what our next term is going to be pretty easy from there. So again, when we think about the general term of our explicit equation, like we had talked about yesterday, we know t of n is equal to that common difference times our term number plus our original starting value. So if we look for this equation, that difference is out in front of our n, which in this case is going to be 6. So if we know our difference is equal to 6, all we need to do is say for t of n plus 1 is that we have our value for t of n, or the previous term, and we're just adding 6 to it. And that would all be all we need to do for our recursive equation. So that's where we're going to stop for today. I'd recommend do 73, do 75 on your own. I'll put the answers in the filled in notes for us for you to double check yourself. But we're going to continue building on this on Thursday as we continue talking about explicit and recursive equations for both arithmetic, like we talked about today, and then also geometric sequences as we go into next week. So I'll leave you with the homework for tonight is 5.2.3. Make sure we take a look at that before we come to class on Thursday. If you have any questions, please let us know. Otherwise, hope you guys have a great rest of your Tuesday. Look forward to seeing you all again in class tomorrow.